Hello everyone, welcome to the complete walkthrough of a machine learning project in Python. We are going to build a breast cancer classification model using the K nearest neighbor algorithm. And this is not just about writing the code, but I'm going to explain every single line in detail, like why we are writing this, what it does, and how is it working behind the scenes. Also, I will explain that how it connects to real world machine learning. First of all, we will start by importing the libraries. At first, we are importing pandas as PD. This line is importing the pandas library. Pandas is a very famous library in Python. It is used for handling structured data like tables, data sheets, or CSV files. And even though we are not using directly it anywhere, but it's often included because it is the standard tool for data manipulation in Python. We can also think it like Excel because it helps us filter and sorting and analyzing data easily. Then we are importing this NumPy and then this scikit-learn. From scikit-learn, we are importing load breast cancer. This line imports a built-in dataset from scikit-learn. The breast cancer dataset contains measurement of tumors and whether they are malignant or benign. Malignant means cancerous and benign means non-cancerous. It's a clean and labeled data which we also use for classification. And internally, this data set is stored as a NumPy array. So even though we don't import NumPy directly, it is working behind the scenes. Then from scikit-learn only, we are importing train, test, and split. And as the name says it all, train means to train the data, test means testing the data, and split means dividing the data or splitting the data into training and testing. Means some of the data would go for training and the rest for testing. Generally, we use the test size as 0.2, means 80% of the data would be trained and the rest 20% would be tested. We use it generally, but also we can use it like test size could also be 0.3 or 0.4. But we should try to minimize the test size because more the data would be trained, more would be the accuracy. Say if we use test size as 0.5, then means 50% would be trained and 50% would be tested. 50% for training is too less. I mean, if only 50% would be trained, then the accuracy would be definitely low because we do not have trained the data with all the possible permutations and combinations existing. So 0.2 is generally standardized. It's a very important step in this whole overall machine learning overflow. If we don't split the data, we risk overfitting because the model memorizes the data instead of learning patterns. Then again from scikit-learns, we are importing standard scalar. This standard scalar is used to normalize our data. And why we have to normalize the data? Because KNN is a distance based algorithm. If one feature has values in thousand, another in decimals, then the larger one will dominate, obviously. But scaling would ensure that all features contribute equally to the distance calculation. And behind the scenes, again, this is using NumPy to calculate mean and standard deviation for each feature. Then from scikit-learn, we are importing the main thing, which is the K neighbors classifier. This is our actual machine learning model, like the K nearest neighbors. It predicts the class of a data point based on the classes of its nearest neighbors. We will use it to classify tumors, whether they are malignant or benign. Sorry. KNN doesn't require training in the traditional sense. It stores the training data and uses it during the prediction. We are using K as 5 in this particular example, which means we will look for 5 of its nearest neighbors, the nearest neighbors of the input data. And we calculate this K nearest neighbor using Euclidean distance. Means from the input data, we would be calculating the distance of its 5 of its neighbors. And among them, the most frequent would be the answer. If none of them is the most frequent, all are in the same order, then we would be calculating the average of all of them to get our answer. Uh, then from scikit-learn, we are importing this classification report, accuracy score, and this is not completely visible, but this is confusion matrix. They all are evaluation tools, which is again a very important step. They help us understand how well our model is performing, not just in terms of accuracy, but also precision, recall, and there is one thing which is known as F score, which is a balance between the precision and the accuracy, or we could say between the precision and the recall. Accuracy will tell us how many predictions were correct, and precision will tell us how many predicted positives were actually positive. Means we could predict as something which was negative, but we predicted it positive. So again, it would be wrong. So it was not very precise. Recalls tells us how many actually positives were correctly identified. And the confusion matrix breaks it all down. Then we would be loading the data set. Data equals to load breast cancer. In X, we are putting data.data. In Y, it's Y data.target. This line loads the breast cancer dataset into the memory. In this example, we are using 569 samples around, each with 30 features like radius, texture, perimeter, and each sample also has a label. 0 is used for malignant and 1 for benign. And as I earlier told, malignant means cancerous and benign means non-cancerous. This data is stored as a dictionary-like object. Dictionary means storing as key value pairs with keys like data, target, and feature names. Here we are separating the features and the labels. X will contain all the input features, the measurement of the tumors, and Y will contain all the output labels, the diagnosis. This separation is standard in machine learning. Generally, input goes into X and output goes into Y. Internally, both X and Y are NumPy arrays, which are used for optimization. Then we would be splitting the data, as I earlier told that it is a standard thing, using 20% the data of the data for testing and the rest 80% for training. This random state 42 will ensure that the split is in the same way every time we run the code. And for reproducibility, it is the most important thing because we want the same accuracy score to appear every time. Training data will be used to build the model and testing data will be used to evaluate it. Then there is this scalar equals to standard dot scalar. Here we are creating a standard scalar object. This tool is actually helping us out to scale our features. So they are all on the same scale. Without scalar features with larger ranges would dominate the distance calculations in KNN, as I earlier told. So they should all be on the same scale. Then xtrain equals to scalar dot fit transform xtrain. This line fits the scalar to the training data, meaning it calculates the mean and standard deviation and then transforms the data. Each feature will now have a mean of 0 and a standard deviation of 1. This helps us the model treat all features equally. Then in next test, we will put the value scalar.transform x test. This line basically helps us in the transformation to the test data. We don't fit again, we use the same scaling parameters learned from the training data. So it is basically ensuring the consistency between training and testing. Then we are training the model. We have created a KNN classifier with 5 neighbors. This means the model will look at the 5 closest data points to make a prediction. And we can experiment with different values of K, obviously, but which works the best for the model. Here we are, for just an example, we are using 5. KNN doesn't learn parameters. Basically, it simply stores the training data only. Then KNN fit X train Y train. This line trains the model using the scale training data. Now the model knows how to classify tumors based on the measurements. Basically, it's just storing data. Yes, it's just storing data. Then we are making predictions. Now that the model is trained, We use it to make predictions on the test data. For each test sample, the model finds the 5 nearest neighbors in the training set and predicts the most common label, which I earlier told the most frequent one. And this is where distance calculation happens using Euclidean distance by default. Then the most important steps comes out, which is evaluating the model. First of all, we are here to print the confusion matrix, which shows how many predictions were correct and where the model made mistakes. It breaks down true positives, true negatives, false positives, and false negatives. And then there is a classification report. This gives us precision, recall, and F1 score and support for each class, which I earlier told. It's a more detailed evaluation than just accuracy. In medical diagnosis, precision and recall are especially important to actually diagnosis of the underlying disease. Now, printing the accuracy means the percentage of correct predictions out of all predictions made would be printed. And this accuracy tells us how much our model was actually correct. So there would be an accuracy score after this code.